Hello and good evening and welcome all to this evening's webinar, Problems Worth Exploring Part 2. I wonder, we've got a lot of people enrolled and online this evening. I wonder how many of you also were there for the Problems Worth Exploring Part 1. Our presenters for this evening. Carol Moore will be presenting second up this evening. Now, Carol is a long-term T-cubed trainer, teaches teaching with technology. She says here that she's been teaching mathematics since the days of log tables. I think a few of us can actually lay that claim, Carol. I know I can indeed. I thought it was most interesting when we first got scientific calculators that we used them to look up logs and anti-logs that were then part of the process of multiplying numbers. I think there was a strange sort of irony in that, but we still taught it. And now teaching at university, so her influence continues on. Peter, now many years teaching and now also working with Texas Instruments as training and support for the T-Cube team and teachers. And he's got 20 years of teaching up on the clock of maths and physics. He's, every time I see, very passionate about CAS, as he says. Every time I see Peter or talk to him, he's always got another problem that he wants to tell me about, whether it's filling glasses, whether it's goats that are tethered and how far they range to. Peter, I do have a goat. I have it cornered. I have it tethered to the corner of a goat house, and with interest I try to do those calculations that you tell me about. But what have you got for us this evening?
Well, the one that I'm sharing with everyone this evening is called the Hailstone problem. Now, it does actually go under several different names. So some people might have heard it as the 3n plus 1 problem. Others may have heard it as, I think, Collat's conjecture would be the correct term. Carol might tell me if I'm wrong there, but Collat's conjecture is another one. So here's a basic description of the problem, and I actually had the pleasure of doing this problem with some students at Emerald Secondary College today, and I'll enlighten you on one of the very articulate responses that one of the students had in their solution, which was very nice. So here's the simple part of the problem. We pick a number, and this is a restricted set that I'm doing here. We'll extend it in due course. Pick a number between 1 and 100, and if it's odd, we'll multiply it by 3, then add 1. If it's even, then we shall divide it by 2. And we repeat this set of instructions until we reach 1. So that's the nice, simple little problem. So let me just drop onto the calculator. And if we were starting this with the students in a nice, simple situation, we could say, well, let's pick a number such as 20. It's even, so we'll divide it by 2. It's even, so I shall divide by 2 yet again. Now it's odd, so I'll times my answer by 3 and add 1. It's even, so I'll divide by 2. It's even, so I shall divide by 2. And so we go. And it appears as though our gentleman Collatz was correct. We ended in 1. But he takes one step further and says we will always end up with 1. So this procedure that I've gone through here develops a sequence. Now once the students start to do that, the actual process, those steps of multiplying by 3 and adding 1, dividing by 2, become relatively trivial. So the students would like a faster way to get from point A to point B, particularly when I challenge them with the question such as, what's the longest sequence you can generate for any 2-digit number? And of course, could you prove it? Well, then that would require us to test all the 2-digit numbers, but also want them to have a look at some of the patterns that are generated. So I'm going to share with people the code because it's a good coding exercise if you want students to write the mathematical code. Now I've added some extra bits, but they're not entirely necessary. It depends on what parts we want to see. So here's the essence of the program. Ignore this little command about the augment thing. So we start by just requesting a number, and we'll assume that Collatz is correct in saying that the sequence will always end up with a 1. So in other words, while my number is bigger than 1, then I will produce these two operations, multiply by 3 and add 1, or divide by 2. And here's the decision-making part of our program. Mod n2 equals 1. Now that actually says the number would be odd. Now the easiest way I've found to teach students about modular arithmetic, because we don't want to focus too much on it, is to say to the students, what time will it be 25 hours from now? And most students will spit out, they'll look at their watch briefly, or their phone, and then they will spit out the time very quickly. And I said, well, that was really quick. So this was about 9:30 this morning, and I said to the students that returned the answer of 10:30 almost instantly, I said, wow, that's impressive. So you said there's 12 hours from lunchtime to midnight, plus another 2.5 hours between now and midday, and the students are shaking their heads and said, really? How did you work it out? And they said, well, it's just 1 hour more than what it is now. And that's modular arithmetic, or as we called it in primary school, remainder. But we like bigger terms in high school, so we'll call it modular arithmetic. So if the number's even and I divide it by 2, it gives me a remainder of 1, tells me it's odd. So I do that procedure. And the only other option is that it's even, so therefore I'll divide by 2. And it repeats those steps while n is bigger than 1. And we display it along the way. Now I've put a little wait command in here, otherwise the program just runs too fast and we really don't see what's going on. So let's jump back to the calculator page, and on the calculator we can see I've left some of the variables for students to use in here, but I've called this one Hail, and here's our request. It says what number would you like. We'll start with 45, why not? And you can see it's now starting to produce the sequence. Now, as I said, if I told it to go through at full speed, you really wouldn't see much of what's going on. And it says that had a length of 17 terms. Now, Carol suggested to me earlier on that I include a nice little graph of this, and I thought that was a good idea. So we'll have a look at the term and the value in the sequence. Let me just change that to a connected scatter plot. And Carol pointed out a lovely little question to our students, which I asked in a different way, but I like the graphical way that Carol suggested, and that is, why is it that with every up, we're immediately followed by a down? So we went from 45, we went up, and then we go down. We get to 17, then we go up, and then we come back down. We get to 13, we go up, and then we go down. So we can see these periods of up, down, and we also notice, as a mathematician, there's a nice little curve happening here which looks sort of exponential. So I thought that was a nice way that Carol sort of put it, is to say, well, why does the graph immediately go down after each up? The way I'd ask the students was, why is it that after every odd number, we end up with an even number? So this particular student from Emerald said, if you multiply two odd numbers together, you have to get an odd number. I said, oh, why is that? And she said, well, neither of them are divisible by 2. Very sort of nonchalant, that's it. I thought that is a lovely way of describing it. I said, so why would we get an even? She said, well, then you add 1, so it has to be even. But of course, there's a nice bit of algebra that sits in there as well, that if we multiply two odd numbers together, and I'm going to use now I won't use n because that's being used already, I'll use x. So 2x would be an even number, 2x plus 1 would be an odd number, and then we can multiply it by some other odd number and take out a common factor of 2. So we can see that these things work when we multiply two odd numbers together. Or in our case, we multiply it by 3 and add 1. So we're at an odd number, times by 3, add 1, and we get that expression. And we can factor that, but I'm not going to type in the whole thing. I think most people here can see that that's a multiple of 2, but we could ask the students to factor it and see that it's divisible by 2. So that's the first part. We get these nice little patterns, and the students can explore different numbers, and they can hit this with trial and error. Oops, let me pick it up from the variables. So let me try another number. Let's say I'm going to try for 87. It's interesting because the students tend to jump to these sorts of numbers very quickly as well. Oops, I don't want that. 87. Now the reason why this is called a hailstone problem is you'll notice that every now and then the numbers jump up quite high. So we had a 500 and something in there, and we look like we're going downwards now and we're heading towards the bottom. So we got up to 500. It kind of oscillates up in those numbers before it comes plummeting down. A sequence length of 31. So part 2 that I've got here, I added to the program a little bit and said, well, once we've kind of found these patterns, and there are lots of patterns in this for students to explore, if we want to get to this idea of, well, what is the biggest sequence that we can get? So this one says, well, where would you like to start? And where would you like to finish? So I'm not even looking at the numbers this time. I'm just generating the sequence length in each case. And I'll put in, and this is where our statistics comes in, we'll put in our data and statistics page, and we'll put our starting number and the sequence length. And the first thing that strikes me is this extraordinary gap in the middle, and I want to know, does this sort of gap continue? We can see down the bottom here the shortest sequences are 2, a 4, there was an 8 in there somewhere, there it is, and a 16, a 32, 64, and if I did some more, we'd see 128. So they're 2 to the end. So our shortest sequences form a nice pattern, just 2 to the end. Here's our longest sequence, and not surprisingly at 97, which then has students starting to pose some other questions. So let's have a look at the sorts of questions students either have posed or we can pose to students. Let's just move on there. So these are the sorts of things. What is the longest sequence or the biggest sequence for a 2 or 3 digit number? And this is what often comes up as a result of our first exploration when I ask students, so why did you jump up into the 90s? And their idea naturally was, well, the bigger the number, the longer the sequence. I said, well, not necessarily. And I'll throw them something like a 256, which gets them down pretty quick, of course. And they said, oh, we thought it would probably have to be an odd number, and it would probably have to be prime. I said, oh, that's interesting. So therefore, do you think prime numbers create longer sequences than composite numbers? And instantly you've got an opportunity for students to go off and explore and collect evidence about whether or not that would be true. Here's one that I picked up from a teacher in South Australia. Do any sequences have the same length as the starting number? Now, I'm going for the 2 trivial solutions, and if anyone wants to send some answers in on the chat, if you find one, not meaning to distract you from the rest of the problems, but first one would be 1, well, that has a sequence length of 1. 2 has a sequence length of 2, because it says 2, then 1, and I'm after, is there another one? How many are there? So, any sequences, do they have the same? I know, hang on, let me just go back here. Let me show you one that's quite close, just to give you an idea on what we're looking for. If I go back to the start, where we're just looking at the numbers, if I type in 25, for example, you can see it's got a few terms in its sequence. And the total length of that sequence is 24. Missed it by 1. So if that had a sequence length of 25, I would have just found another answer to my solution there. So next one, what's the ratio between odd and even numbers in a sequence? So if we think about Collat's conjecture as, well, 50% of numbers are odd, 50% of numbers are even, the odd rule says you go up much faster than what you do for an even number, which heads you down quite slowly in comparison. We're dividing by 2 compared to multiplying by 3, and yet we always seem to go down. So that tells me, and a really simple question, well, relatively simple question I should say, is would we ever get any sequences that contain more odd numbers than even numbers? So I don't think people will spend much time thinking about that. The logic dictates the answer very quickly. We should always have more even numbers in a sequence because otherwise it's going to spiral upwards and collapse would in fact be wrong. But it did lead me to some other thinking. So we've seen the hailstone problem number 2, and I'm just going to move along to hailstone. Oh, by the way, that pattern that you see there sort of discontinues very quickly, because if we go from 100 to 200, you'll see that it starts to get cloudy in the middle again. So as mathematicians are often looking for these patterns, so Hail version 3 includes some extra stuff. So if I start from 1, and let's say we'll go up to 100 again, that's worked out all the sequence lengths. That's not a sequence in itself, obviously. So let's have a look at the sorts of data that I collected this time. There's a mess of stuff here. I could do the number versus the length. That's what we saw before. But what if I looked at even? Doesn't make much difference, really, does it? So I'm looking at the starting number, how many even terms are in there, and how many odd terms are in there. Not much happening there. What if I have a look at even numbers versus odd numbers? Whoop. I think that's pretty cool. That's something that seems almost completely random, and we see at the very start here where we're kicking off these sequences, it's a bit messy, but as we get further along, they're getting quite linear in there. There's a big gap in the middle, we know that. So let me just go back, and this time we will run the program going from 100 up to, let's say, 300. I can't remember where my buffer was to say it's too many. It will take too long. So there we go. It's worked out all the sequence lengths between 100 and 300, analysed the occurrence of odd numbers and even numbers, and let me just zoom in on that data to make sure we've got it all. There it is. That's remarkably linear. And if I was interested in, say, finding out the equation, whoops, that's not the one I wanted. Menu, Analyze, Regression, let's just do a linear one. The correlation coefficient is remarkably high. It's almost perfect. So my question then is, what's this ratio all about, and does it stay at 0.629? If I investigate numbers in the thousands, do I still get this ratio between odds and evens as about 0.629, and what's that all about? And there's a nice algebra that sits behind that as to what that ratio might tend towards. Of course, none of this actually proves that collapse is correct, but I'm actually not trying to do that because there's been plenty of mathematicians go by before me that have not managed to do this. In fact, it is one of the many unsolved mathematics problems. So looking at ratios between odd and even is pretty cool.
Oh, come on, Foxy, you can do it.
Oh, I wish I could, Brian, but
You're the man.
That's it. Here's another one. Which numbers can be approached from above and below? Now, what I mean by that is, say, for example, if we look, and this is where the programs kind of miss out a little bit when everything's done for them, is we still need the students to go in and do the by-hand manual calculations to look for these patterns. So, for example, when the students were doing it by hand, and I said, well, let's see if we can find the biggest two-digit number, this is the students at Emerald today, when I said to them, well, see if we can find the longest sequence, and then another one of the students had said, well, I don't need to investigate 45 because we've already done that, but then I don't need to look at 20, 16, 8, 10, and she said, I don't need to look at any of those numbers in that sequence because I already know where they'll end up. And I thought that was quite clever. And then we noticed that 10 appeared in several different sequences, sometimes coming from above. So, for example, if our sequence produced the number 20, we could land on 10. But if our sequence produced 3, being odd, then we multiply by 3 and add 1, we get to 10. And not all numbers can be got at from above and below. So that's why that's an interesting question. And I'll give you a quick heads up. 10 works, 16 works, and 22 works, and 28 works. So all of those numbers can be approached from above and below. So what I've given the answer, but I want students to figure out why, because there's a lot more going on here. We want to know why do these things happen. So that's another one students can investigate. And then if you've got more ideas, and that's one of the beauties of this problem, is students come up with ideas on what they can research and how they can present their information. So as a problem for, say, Year 7 or 8 mathematics, or even all the way up to Year 9 or 10, I think there's enough in here to have students going. And the fact that there's no endpoint, per se, that is, as I said, it's a conjecture that's never been proven, and I'm not expecting, obviously, a student to prove it, although it would be nice. I think it's a good problem that they can explore and get their teeth into do, and do a lot of mathematics that sits there between it. Particularly this one. This is where your Year 10 maths really comes in, if they start using their algebra to try and come up with this ratio. Is this some new, I'm not going to call it a golden ratio, I might call it a Hale ratio. Does that have some sort of a value to it? It looks kind of like the natural log of a number, for example. It's not, but maybe there is some pattern to it. And it's certainly cool that we get this really strong correlation. And as mathematicians, we know whenever we get a strong correlation like that, there's normally some meaning behind it, and there is. So getting students to explore that. All right, so that's my hailstone problem. I have lots of others, but right now I'm watching the time and thinking it's time for me to hand over to Carol, because Carol has some great problems to solve as well. So let me just transfer over to Carol. Yeah, look, I do like that problem.
Yeah, a classic example of those sorts of things where the accessibility is the access level, initial access level, is quite low. Like anyone can get into it.
Exactly right. Yeah, and the one, the first I heard of it, yeah, the first one I heard was giving it to students in grade 5. And I thought, well, that seemed ambitious, but then, like you said, Brian, that there's nothing at the start, just the actual algorithm, there's nothing there that a grade 5 student couldn't do.
Yeah. And then you probably wouldn't discuss correlation coefficients with them.
No.
No.
Not likely.
But so good that, the further you get into it, you ask more and more questions about it. Something that's initially starts so simple.
And as I said, these students today, they were coming up with some absolute pearls of wisdom when they were describing what was happening and why it was happening. They didn't necessarily do any algebraic proofs thereof, but their literal interpretation was pretty spot on.
Yeah, and the conversations are so good, and which in itself is a lovely assessment tool as well, or can be. Yeah. Can I just point out to everyone, the problem that Peter's demonstrated there, that can also be done on the TI-84 that you now see on Carol's screen. Likewise, the problems that Carol is going to demonstrate can also be done on TI-nspire. So whichever platform you're using, you can take these problems and adapt them accordingly. So Carol, what's happening with the pi? I like pi.
Like pi, do you? That's good,
Yeah.
thank you.
My favourite number.
Just going back to the hailstone problem for 1 minute, one of the things that intrigued me about it is why multiply by 3, then add 1. And what's interesting, I've messed around with it a bit. If you get an odd number and simply add 1, it becomes even, then you can divide by 2. And I've tried a whole lot of numbers, and they seem to come back down to 1 as well. So I'm not sure what the significance of the multiply by 3 is. So that's another thing that students can investigate as well, of course, or multiply by 5, or perhaps by any other odd number.
Well, the one, I don't know whether you've heard of this one, Carol.
Beg your pardon?
The nice one I heard was once students are convinced, and they usually say by stealth, we've proved that it doesn't, that it always ends up with 1 because we've tried all these numbers and that seems to work. You say, so what do you think if we did 3n minus 1? Would that have any real significant impact on the outcome? And the majority of students go, no, we'd end up with the same problem. And in fact, it falls apart with a 2-digit number very early on in the piece, which then stimulates them to go on and see if they can find one that doesn't work, because it just seems bizarre they're doing 3n minus 1 would fall apart, and 3n plus 1 never falls apart. And people need to remember, by falling apart, it could get stuck in a loop, which is what happens with 3n minus 1. You get stuck in a loop, and therefore you never get out of it and don't end up with 1.
And so you shouldn't adapt your program. You shouldn't adapt your program that does it.
Somebody's left their phone on. They've just got an interesting comment from someone from one of our participants from Queensland, who has just pointed out that the conjecture has never been proved, although we do tend to think that there's an infinite set of numbers that will converge to 1.
Yeah. That's right. It's never been proven.
Yeah.
So, yeah, that is the case.
Yeah, I love those sorts of things. How can you prove it and how can you disprove it? Yes.
Okay,
yeah,
so let's get a pie then. So this exercise is called another piece of pie, Monty, which I presume most of you will recognise Monte Carlo method. So what it's about is using random numbers and lists and a test function to calculate the number of points. Sorry, every phone in this house is ringing at the moment. So,
okay.
Sorry about that. So that's what this is actually about, hence the name, another piece of pie, Monty.
Sound booth, Carol.
Pardon?
We need you in a sound booth.
Yes, I'm sorry about that. I can't do anything about it. I'm on the phone from Queensland and he's not giving up. So I'm very sorry about that. But what this actually does is lead us to an estimate of the value of pi, hence the name of the exercise. If you're going to be doing random number generation in lists and so on, it's really a good idea as well, if you're using the calculator, to remember to get students to reseed their calculators so they don't all get the same results when you're playing with random sets of numbers. So the first step in this is to actually produce 100 random numbers and store it in list number 1. So I'm going to do that. So we just go to the Maths menu, Maths, Random, and we just need 100 of those, and we're going to store it in list 1. And that happens, of course, fairly quickly, so the little thing was curling. So these are all random numbers between 0 and 1 to about 10 decimal places, which is irrelevant, but we have 100 of them stored. Now I'm going to do it again, and I need to get a second list, so I'm going to go up and grab my command from there and change it to list 2 and enter that, and I will now have 100 points in list 1 and 100 in list 2, and I'm going to assume that they are the x and y coordinates of 100 points in a unit square. So I'm going to have a look at those in a graph. So we're going to have a look at a plot, and I want it to be a scatter plot, not joined, so that's going to go on and down to that type, and let's have a blue set and let's graph it. So there we are. We've got the 100 points, all with coordinates between 0 and 1, in a little square which ranges from 0 to 1 on the x-axis and 0 to 1 on the y-axis. You'll notice I've actually already got y equals 1 in there. I could put in a vertical line at x equals 1, but because that's a drawing, as soon as I change anything, the drawing will disappear, so I'm not going to bother to do that. So going back to the PowerPoint, so I've got a scatter plot of these points, and Zoom 9, of course, always fits that into the screen, but I set up a window that was appropriate for what I was using here. So I've got my 100 points, and so some of the questions you can ask about this are, well, how many points are above and below that line? So if I go to y equals and put in 0.5 and graph it, I could have students count, and I would expect that if these are 100 randomly distributed points between 0 and 1, then about half of them would be above the line and half would be below. And that's a fairly boring little exercise, but if we go to perhaps something like y equals x, and graph that, that's perhaps a bit more interesting. You'd expect a half to be above y equals x and a half to be below y equals x. But that's really not anything to do with pi that I can see, unless you like pi's cut into two big fat triangles. Similar idea, the similar idea would be if I did just y equals 1 minus x, just as another idea. Have a little look at that. And again, about half above and half below. But if I want it to be something to do with pi, I'm just flicking through these points. If I want it to be something to do with pi, what I've already done in here, you'll notice, is put in, I'll clear that one off, I've actually put in the square root of 1 minus x squared, which will give me a half of a circle, and I'll graph that and have a little look at that.
Carol, I'm just wondering on the Zoom if we can square that.
You can certainly do that. I've done that before, but it messes up where I want the points to be, Brian. So I can do it. If you want me to, I'll do it. Zoom 5.
Yeah, because it now looks a lot more like a
Okay, that was why I didn't. So nothing to stop people doing that, of course. I'll just make it back where I was before. And the y can stay the same. That one's all right. Okay, so I've got my points.
Yeah, so we know what we're seeing. It's just stretched. Yep.
Yep, so we've got a quarter of a circle in the diagram. And as you say, it doesn't look much like a circle, and zoom square does all those things, etc. Okay, so this time we know that the area of the quarter circle is pi on 4, since the radius is 1 unit. And pi on 4 is about, in inverted commas, 0.7835 to a whole lot of decimal places. So I could argue, if my points are randomly distributed, that about 78 out of the 100 in that little diagram will be either on or below the edge of that circle. So I could count them on the screen to check it, but that's a bit obvious that the exercise is not about counting those. But for students, it wouldn't be a bad idea to play around for a little bit trying to count them, I think. So I'm going to do a different function at the moment, and so I'm going to put in number 2, the function y equals 1 over 1 plus x squared. Something I've not used a lot myself, but I notice a lot of students do this. If I use my alpha y equals function to get at my fractions, I can actually put that in quite neatly. I would normally write 1 divided by brackets 1 plus x squared, but I've noticed a lot of students like using this fraction button, so I will use that there now. So y equals 1 plus x squared, and I'm leaving the quarter circle on there as well. And this is what I like about the CE, that of course you get different coloured graphs as you draw them. So I've got a blue, a black and a red on the screen. Now I could always also put in a vertical line at x equals 1, which is there on the right, but or perhaps I'll just draw that just to show you, but it will change as soon as I do something else on the screen. And so I've got my vertical line, shift him across. Very slow doing this. I don't think there's a facility for saying at x equals 1 as far as I know. So you just have to move it. So I'll keep moving. And one of the questions now is whether the area below that red graph, y equals 1 over 1 plus x squared, what do you think that area might be? So just stop for 1 second and have a little think about what you reckon that might be. Do you think, well, according to the dots, there aren't too many dots between the red and the black, but would you expect that the area under the quarter of a circle is about the same as the area under a randomly looking curve 1 over 1 plus x squared? And so my next bit is to actually go to what that actually is by counting the points. So we can count them, but I want to show you how to use the calculator to actually count them. So what I actually need to do in this exercise is check how many points on the diagram have y coordinates, which are L2 in this case, that are less than or equal to the function value. So if I press trace, there's the odd function, that's one odd dot. This dot has a y coordinate of 0.905 with an x coordinate of 0.5, and if I change to the y equals 1, well obviously it's 1, but Now that's x equals 0.5. For the y equals 1 over 1 plus x squared. But if I scroll again, don't want that one. Now, unfortunately, it's not doing as I thought it would do. I expected that this point with x equals 0.56 by scrolling downwards would go directly to my curve, but it didn't, so that's all right. But what I am really interested in is whether or not the y-coordinate of any of these points in here below the thing have values less than the value on the y equals 1 over 1 plus x squared, if that makes any sense. So that's what I'm going to be trying to test. So I'm going to go to list 3, and I'm actually going to calculate the y-coordinate of a point here, or a point anywhere, where I can check whether it's going to be greater than or less than the value that's on the red curve. I might just go back for 1 second and turn off the other one. Turn him off and just go back to my graph again. Okay. So I'm going to try to check whether or not the y-coordinates compare. So I'll go to my list, edit. Now, as a matter of interest, this command does not seem to work on the new version of SmartView. So it's something that TI is looking into because John Bayman and I discovered this. I'm quite accustomed to being able to evaluate functions, in this case y2, evaluated at all of the values of L1. So I'll just show you what I mean by that. So alpha, I want y2 evaluated at list 1. And what this should do is take each of these x values, put them into the y equals 1 over 1 plus x squared, and tell me what the value is when I enter it. So you'll see it's working away there, and it is actually going to create all these points. So this one, for example, I can see that when x is 0.56, the original point that I did randomly had a y-coordinate of 0.9, but on the y equals 1 plus x squared, 1 over 1 plus x squared, it's 0.75. So this point is actually above this one. So I could go down now and have a little look at these and say, well, what's going on here, which one's bigger, which one's less, and so on. But again, I can use the list very nicely for that. So I've got my list, but I only really want to know whether they're above or below. So what I'm going to do is calculate L3 minus L2, this y value minus that one, and store it in list 4 and count up how many values there are, how many ones and how many zeros. Now, well, I won't be doing that for a minute. I'm just actually looking at the values. So this is going to be L3, take away L2, and enter those in. Now, I have a whole lot of positive and negative values, which I actually need to scroll through, and that's a bit of a pain. All I really want to know is how many are positive and how many are negative. And so it's the positive ones where the graph y over 1 plus x squared is actually above the random points. But they're the ones that I'm interested in with this positive difference. So what I'm actually going to do is actually go up and clear that out. And rather than put it on there, I'll go back to the home screen and show you a way of doing this very nicely. Sorry, I need to clear that, don't I? Clear all that out. What I'm going to do is do a test on this. So if you look at list 3 minus list 2, and the tests are all in here in the maths menu, so second maths to test, and I want greater than or equal to, which is number 4, greater than or equal to 0, and I'm going to store those in list 4 now. Now, what actually happens this time is that list 3 minus list 2 greater than or equal to 0 actually checks those values. It'll give me a 1 if the answer is positive, if it's true. It'll give me a 0 if the answer is not true. So if I enter that and pop those into list 4, I've got a whole lot of 1s and 0s have bobbed up. So let's have a look at them in the list. and make sure they've come up in the right place. So list 3 minus list 2 is positive, etc., etc. And so I can check all these points. Now, the only thing I need to do is actually be able to count up all these ones and zeros in there. Now, again, that would be a boring exercise to do as well. And so what I can do is actually find the sum of that list. I add up all the ones and all the zeros, in other words, get all the ones. And so I'm going to do the sum. So that's a statistical thing. It's an operation on a list that I'm interested in, and it's mathematical. So I want the sum, which is number 5, and I want the sum of list 4. It's 77. So in that very roundabout way, I've actually been able to count that there are 77 points on or below that curved line out of the 100. And so what I actually have there is an approximation. I have an approximation there for the area underneath that curve, which is 77 over 100. Now, you might say that's not very close to pi on 4 at least, but if a whole lot of students do it, and if I do it over and over and over, or if I took 1,000 points, or 999 as the list will allow me to do, I will get a better approximation to the number of points under there, and probably it will become closer and closer to pi on 4. And again, do a whole lot with students, and they can do it over and over. But remember again that the student calculators have to be seeded differently. Now, what I'm saying there is the area under that curve, why it was 1 over 1 plus x squared between 0 and 1, is in fact approximately pi. And so I'm going to go back to the graph, and I'm actually going to calculate the area below that red curve. Now that's a second calculate, and it's number 7. But I need to know which curve I'm dealing with. It's that one, y2, it was 1 over 1 plus x squared. 0 is the lower limit, and 1 is the upper limit. And I love the way this does it in colour for me. This turns out to be 0.785, which I think is quite cool. Now, you might say, at what age would you use this with students? Now, I think one of the great things about having this technology in our hands is that we can actually show kids how to do things on the calculator, which doesn't necessarily make any sense to them, but we could show them that this little curly S sign for a function and a little dx, we don't have to worry about what that all means, I don't think, but we could actually show them that that actually calculates this red area, and I think that's quite cool. Clearly, you could do it just on the circle for younger classes, and actually show them if you shade in the area under that quarter of a circle, it is exactly, in fact, pi on 4. And so this is a bit neat that this one actually turns out to be pi on 4 value is about 0.785 again, which I think is nice for older students, but you could use the quarter circle for the younger students at any time. And just to show you, of course, why it is actually pi on 4, just in case if you're doing senior maths, you might be interested in how you actually do the integration of that by hand. It's a trig substitution, and you find that you end up with the answer pi on 4 for that. So
I was just about to say we don't need integral calculus anymore.
if you're doing definite integral, obviously. But
Yes.
a little bit of stuff there, I think. And you can actually, as I just did, get that area in there, and you can actually do it straight on the home screen as well if you want. And one of the little tricks that I like is that if I suspect that this number, 0.7853, is in fact something to do with pi, dividing that answer by pi gives me an exact fraction, 0.25. And I think that's something that's fairly powerful as well. So that if you think it's related to pi, then divide by it. Exact fraction says, yeah, okay, that was in fact pi divided by 4, which I think is pretty useful. And one of the other little tricks that I thought about with doing this particular exercise when I was thinking about integration and areas something that bobbed up was, if you do the integral from 0 to 1, he's back again on that phone, I do apologise for that. Dear, oh dear. If you just have a look at those things on that screen, integral from 0 to 1 of x squared turns out to be 0.333 or 1/3. The integral from 0 to 1 of x to the power of 3 turns out to be 1/4, and so forth. And then I thought, well, what about x to the 0.5? Well, integral from 0 to 1 of x to the 0.5 turns out to be 2/3. Now, why 2/3? Well, hang on, 2/3 is 1 over 1.5. And so forth. And I thought, well, that's a nice little lead in to the idea that you can actually make a conjecture about the integral from 0 to 1 of x to the power of n, and it is in fact 1 over n plus 1. Now, can you prove it? No, you can't. The numbers seem to verify that. But, you know, I think it's quite a neat little idea that I don't have a problem with actually giving students little hooks that they will come to later on when they do the higher level of the mathematics. And so having gone through all of those pieces of pie, I've now cut the pie up, as you can see, and I'll hand it back to you, Jack.
Okie dokie, let's do it. I really like that.
Okay, I'm going to eat my pie.
Eat your pie.
Well, I think we've almost managed to get people hungry for pie, so I'll throw one more in there. I'm just waiting for that. My computer's sort of coming unresponsive. There it goes. It's back now. It's good. So since we're talking about pie and making our webinar participants hungry, I'm going to call this one Buffoon's Needle. It's not, it's Buffon, depending on how much French you want to put in it. It actually comes from a French mathematician called Georges-Louis Leclerc, I think was his correct name. But he owned this town, or at least his father did, and his father sold it and he bought it back, and that's where the problem is named after. But if you haven't seen it before, we've got this one on the TI website, but here's the quick description. The idea is that if you drop your pen on the floor, and coincidentally that the pen or needle, whatever it is that you're dropping on the floor, has the same length as the width between the floorboards, then the probability that it crosses one of the floorboards has a very interesting relationship with pi, other than dropping pi on the floorboards. So we can simulate it. This is just a little simulation that I've set up. And we can count the number of times it hits and keep on going. And students can count the number of hits to see what proportion of those land across the floorboards. Now, you might be thinking, how on earth could that possibly have anything to do with pi? Well, the activity on our website has all the teacher answers in it and the student activities and the TI-nspire file that you see working away here. You can see the little animation of it on our website. But let's have a look at the visual explanation of what's going on. Let me just fast forward a little bit. So what I did is drew a little animation to help people understand, or students understand, the actual problem itself. So here we can see that the pen is not crossing the floorboards. If I swing it around a little bit, we're still not crossing the floorboards. And here's our pen down here. Now you'll notice as I drag it along this way, it's really not doing much to the actual dot that's sitting on the graph down here. But if I rotate it and let's say move it up a little bit, you can see the pen has crossed this line and it's highlighted this graph down here. So let me swing our pen around a bit. So we're graphing the angle that the pen makes with the floorboard. That's one of the things that we're graphing. And also, in a sense, the distance it is from the floorboard in either direction. So, each time I cross the floorboard, you can see my dot either crosses here, or if it's an extreme situation, it falls into this region here. Now I think as people look at that, they might realise this looks some sort of a trigonometric function, most likely. We're talking about angles and rotations and the like. So it's probably got something to do with the area under this curve. Indeed it does. So in the teacher answers that you'll see on our website, there's a diagram there for teachers and students to use to help set up the actual equations to work it out. So what we're saying is we've got some pen or pin of length L, which is the same as the distance from the top and bottom parallel lines there. And if this length here, or rather this one here, if that is less than D, then we will cross, or the pen will cross. So as it says down here, if D is less than, and we can work out this length here from P to the outer point on this circle, it's just the pen rotating. If that length there, we'll define that as L on 2 multiplied by sine theta, that will get us that. And if that is, if that distance is less than L2 on sine theta, then the pen will cross. So we can see that we've got some trigonometry happening in it already, and then we can actually use a little bit of calculus. Now I'll let participants go on and read that entire document for themselves, but needless to say, get it? Needless? Oh, bad pun. Sorry about that, Brian.
Okay.
It was a bad one, wasn't it? All right. So, needless to say, and I'm sorry, I can't stop saying now, the solutions and the actual problem lead us to 2 divided by pi. So, it's a flip on what Carol had, because mine's upside down. It's 2 on pi, and Carol was doing pi on 2 and pi on 4. But again, another nice example of pi popping up in mathematical explorations. It's another good one too, because it follows on with what Carol's saying, is doing some simulations and probability to, and in fact, this George Louis Leclerc was the first person to kind of put integral calculus and probability together. So it's a nice sort of connection with what we've been doing tonight.
Did he design the Forth Bridge in Edinburgh?
What was that one, sorry?
The graph looks, it reminds me very much of the Forth Bridge.
Not yes, yes, I know what you mean.
Yeah, crosses the Firth of Forth.
Yes.
Just north of Edinburgh.
Right. I'm looking at the time thinking we're almost out of time, so I'll hand back to you, Brian. Okay. I haven't seen any more questions coming in on the chat there.
There we go. Can I share one as well? Foxy, with all your graphs that were moving up and down, it made me think of one that I did just earlier this week. I'm in the business of brewing beer and putting it into kegs, and I've acquired a deep freeze, which I can store kegs in, but I obviously don't want to freeze my beer. So what I'm doing is I'm putting the temperature probe. I'm using the calculator, and I'm putting the temperature probe in. That's the just the auto-sense temperature probe, stainless steel probe, and I've got a timer where I'm switching this thing on and off as we go. So I keep messing with it to try and damp that down a bit so that I hold the temperature within a specified couple of degrees. Problems worth exploring.
That's pretty cool, Brian.
Yeah. A cool diversion. Yes. Okay. Righto. So the closing... So the closing slides, the follow-up after the webinar, you saw a preview of these earlier on, did you not? But stay tuned to an email box near you where you will be getting the links to the webinar to download if you wish, but also the materials, including those programs. I might once again point out that the programs can be used on both platforms. That's Inspire and the TI-84. And Carol's Monte Carlo activities I really like, particularly because I'm a fan of probability, and the Monte Carlo one I have used since I first saw it. I've used it with just about every integral calculus class that I've taught, at some stage, just to point out that these things can be done by another approach other than just integral calculus, and you do get some good Brood A tomorrow, you can see there, and you do get some fairly convincing results. Carol, I've done that on the TI-84 and I've done it on the Inspire, and I actually prefer it on the TI-84. I think it's more, shall we say, tactile on that. It seems to make more sense. Yeah, easier to see, I think. Okay, so enough of my ramble. Please fill in the feedback as the webinar closes. And can I point you to some other wonderful things, the Teacher Centre that Peter just showed you, where we've got some great activities for senior Australian Curriculum Inspired and Senior Curriculum Inspired. And you can download the entire lesson packages. You get worksheets for students, you get answers for teachers, you get the corresponding calculator files. You can also use test and assessment equipment files that are there, or you can just direct your students to it where they can watch tutorials on topics that are listed to and directly linked into the courses of their study, particularly further maths methods, specialist maths, and many of them actually prefer to view a lot of that sort of stuff on our YouTube channel. You see the link there. Some wonderful materials on there. Can I give a plug for a couple of conferences coming up? Next week, next Monday and Tuesday in Fremantle, there's the Mathematics Association of Western Australia, if you're over that way, the MAWA conference, and T-Cubed will have a presence there. And on Friday next week, a STEM conference, middle year STEM conference in Adelaide, and Carol, Peter and myself will all be in attendance at that one. And then if you're in Victoria, the following Tuesday we have a Learn Energise Connect event at Mount Waverley Secondary College. That's on Tuesday the 29th of November. So face-to-face PD to supplement all of the online PD that you have been doing. Of course, the T-Cubed team will also have a strong presence at the MAV conference at La Trobe University. If you can't get along to any of that, please at least subscribe to the newsletter, where you will get lots of ongoing information and ideas, and if you have questions about, please call. Thank you to participants this evening, and particularly also to our presenters this evening, Peter and Carol. So without further ado, I wish everyone well for the forthcoming holidays, getting everything sorted before the end of the year, and we hope to see you joining us again in the new year for our 2017 webinar program. Good evening all.
Thanks, Brian.
Thanks, Brian.